Okay, so hello everybody. Welcome to tutorial number 5 of cognitive robotics. Today we're going to discuss temporal and numeric planning using again the unified planning framework that we learned last week. First, just a few announcements in terms of the course. So after realizing that there have been a few, say, Python and general computer issues in the last tutorial, I've created an environment YAML file that you can install as such that will give you the problem packages. Thank you, Esther, for helping me realize the problem and set it up. So if you're having any issues with the versions of the unified planning framework or anything with your Python, it's really not working, you can use this guide here, install Uniconda, create the virtual environment that contains only the packages we need and the version of Python that we need, which is 3.8.8. And that will ensure that you can run tutorials the same way that I do, and we can ensure that everything is running smoothly. If you don't need it, you don't need it. It's just a helpful thing that will be probably useful for the homeworks and for the tutorials. If anybody here is using Mac and still running into problems, please let me know. I'm trying to work on figuring out what to do with Mac computers. I use Windows, and I assume most of you are Windows, so for most people it's not a problem, but we'll figure that out. And if your Conda doesn't work from inside VS Code's terminal, let me know. I'm also working on that problem right now to see if we can solve it. Regardless, the first homework will be released tomorrow. It'll cover everything we've learned in the first 5 tutorials, and it'll be due 2 weeks from tomorrow. So December 15th, that's the last Thursday before Hanukkah. I don't want to have you working over Hanukkah if you don't need to. Should be plenty of time. You can work in pairs. You can do also singles if you prefer. But this way you have some first practice actually working with United Planning Framework. And I won't have any more work for you over Hanukkah. If you want an extension over Hanukkah, you can ask me, feel free. I just prefer not to require for everybody to do it during their break. So that's it. Any questions regarding anything involving the course? Anything? Awesome. So we can begin today's tutorial. Oh, just a last thing. So I figured out how to make Windows subsystem for Linux work for me. So because next week we're going to be doing our first Linux tutorial, we'll have a guest speaker, Amichai, who's the lab engineer. And we're going to be doing our first Linux tutorial in the tutorial class. It'll only be on Sunday. Wednesday, there will be no tutorial. It'll be recorded, of course, so whoever can't come on Sundays, you can just watch the recording. By then, you should try and have some way to access Linux on your computer, whether it's with the SSD cards, whether it's using a VM. If you want to have Windows, and I see that the Windows subsystem for Linux is quite easy to install and quite easy to use. For example, if I just open my Windows PowerShell and I type in WSL, I'm already in Linux. This is an automatic Linux virtualization that Windows has enabled finally, and it finally works decently, better than any virtual machine. Not as well as the SSD cards, but it's better than any virtual machine available on Windows, I think. So feel free to use that if you haven't bought the cards. If you don't want to, I think it should be fine for the purposes of the course. Okay, so today we will be, let's have this, discussing temporal planning and numeric planning. So up until now, we've been dealing with problems that aren't so realistic. We've been doing classical planning where we just assume that every action occurs instantaneously and actions can only occur one after the other. We've also looked at cases where the description of our world, the properties of our world are Booleans. We haven't looked at any numbers or anything like that. So now we want to look at problems that involve planning, where it might be more relevant, more useful to represent our world using numbers, using real numbers, integers, or using time, using durations for our actions. So after PDDL 1.2 came out in 1998, that was the kind of first version of PDDL, which only dealt with classical planning. 5 years later, in 2003, they came out with PDDL 2.1. I don't know what this numbering scheme is, but that's what they came up with. And PDDL 2.1 is just an updated version of PDDL that allows us to represent temporal and numeric problems. So the syntax is the same. There are going to be a few new functions and things that we can define, but essentially anything that was valid in PDDL 1.2, any commands, any files, any plans are still going to be valid in PDDL 2.1. So we won't have any, say, dependency issues working now with PDDL 2.1. So we'll go over a bit what's the new syntax, what are the new things that we can do with PDDL 2.1. So one of the first things that we can do is now define, as I said, numeric variables. So the general term for the variables in a planning problem is a fluent. We've already seen predicates. Predicates are examples of Boolean fluents. They're fluents that have a true or false value. Now we have numeric fluents, which can take on the value of real numbers or integers. So if I want to create a new PDDL 2.1 domain file, I can add something called a functions group and declare a bunch of numeric fluents there. It's a similar formatting to how we declared predicates before, but now we can see that we have, for example, I have a numeric fluent called battery amount. This this fluent is equal to some number, and here I've attached it to a rover. So I can attach it to a specific object. So I can check for however many rovers I have in my problem. I can check the battery amount of that rover throughout my plan. Similarly, I can use numeric fluents that don't have any parameters passed to them. They're general fluents. So for example, say I have a fleet of rovers and I want to know the total distance traveled by all of the rovers together. I can just call a general numeric fluent called distance traveled, and I'll update that accordingly. And I don't have to associate it with any specific rover object. To change these numeric fluents, I can do a few operations. As you can imagine, I can do addition, subtraction, multiplication, and division using the common symbols for those things. I can also use keywords, so I can say increase, decrease, scale up, scale down. And I can assign a new value to a fluent using assign. So I can just give a new value that I decide to one of my fluents. The nice thing is that I can update any fluent's value in reference to a different fluent's value. So for example, if I want to, I can either assign the number 10 to my battery level, or I can even assign another numeric fluent called max charge to my battery level. So I can pass a different fluent as the value of one of my fluents, or I can just pass some numbers. And it's the same for all of these mathematical operations. You can pass a number or a fluent. In my states, you don't put the addition and subtraction in the state, but be the effects of the goal. Not a goal, effects of an action. If I'm looking at the states, the state of the world, obviously those operators aren't relevant if I'm looking at just the state. But if I want to assign a value to my fluents in the initial state, for example, I can use an equality. So I set the battery amount for rover 1 equal to 100. In my goal state, I can do similar things. So I can also use equalities, and I can also use inequalities. So I can say that in my goal state, I want to have my battery level, my battery amount be greater than 0, at least. Any questions on this so far? Awesome. Now we can add some temporal effects to our problems. So we have something called durative actions. So until now, we've only been looking at actions that are instantaneous. Now we can assign some sort of duration to our actions using durative actions. So we declare using the durative action keyword, we pass parameters again. And this time we have another feature for the actions called duration. So here I can set the duration, how long will this action take up? And I don't have to specify the units. It's just some unit of time, 5, whatever unit of time you want to use. It's your job to keep track of that when you're representing your problems. PDDL won't do that for you. The duration doesn't have to be fixed, so I don't have to say it's 5 units of time exactly. I can create bounds. So I can say it'll take between 3 and 5 seconds, for example, if I use inequalities. And now, one of the important differences to note when we're talking about durative actions is that we no longer have preconditions, we have conditions. So I can assign a condition to conduct the durative action based on some value that must be true at some point during the action. So preconditions only care about what's true before I start the action. Now with durative actions, I can have conditions that depend on things that happen during my action. So for example, say I have a battery level equal to 5 right now, and I want to drive my rover, but it requires 8 level to actually reach there. Or there's some, say that's not a great example, let's say it requires 4 battery to reach that place, but somewhere along the line, my battery level will for some reason drop. And I didn't account for it before. So using a precondition there, I wouldn't know that my rover is going to fill along the way, but here I can add conditions that I'll check along the way if certain conditions keep holding. So I can add conditions at the start. So for example, if I want to move my rover from one location to another, I just add that at the beginning of my action. I have to make sure the rover is at the from location. Now I can add something called an overall condition. So this checks that for the entirety of my action, this must be true. So I must be able to move, can move from and to. And that must hold from the beginning to the end of this action. And I can also use a numeric variable in my conditions. So I can say that at the start of this action, my battery amount must be greater than 8. So here I represented the inequality greater than 8 in the fluent that I'm talking about. Then in my effects, I just call them effects because they are similar to the effects in instantaneous actions. But this time I can add effects that occur immediately after the beginning of the action, throughout the action, and at the end of the action. So I can specify also different time points for my effects. So for example, once I've finished moving my rover from to 2, I have the effect that my rover is now at 2. That's only at the end. I've also added that my rover will have been to the 2 location once it actually arrives there, so at the end. And now I can actually add an effect that applies immediately after the start of the action. And that effect is that my rover is no longer at from. So you can think of it like if my rover starts moving towards a different location, immediately as when it leaves, it stops being at the original location. So here I can actually state that that's one of the effects of this action. And again, I can use numeric effects. So I can decrease my rover's battery amount by 8 once it begins its action, and I can increase the total distance traveled at the end of the action by 5. Here, this at start effect isn't so realistic because the battery in a rover wouldn't drop by 8 immediately. It's not really a realistic way to model battery decreases. So to do that, we could use something called continuous effects. So these are effects that change over the course of the derivative action. So for example, I could have my battery, my rover decrease at different time steps over the course of the whole action rather than instantaneously. The battery level will decrease, for example, by 5 at every time 1 unit of time passes. So here, use hashtag T's, that just says for 1 unit of time. So here I increase, for example, my fuel in the tank by 1 unit for every unit of time that passes during the action. And as I just explained, for my battery level, I can decrease it by 5 times the unit of time that's passing throughout my effect. So if I check throughout at any given moment in time during my derivative action, I will see that battery level and the fuel will be at different values and they'll keep changing over time. Any questions up until here? Awesome. One last thing is metrics. So up until now, we haven't really discussed how to specify optimality in dealing with our problems. Most of the time, we'll just assume that the minimum number of steps is what's optimal, but there are different ways to clarify what's actually optimal. So my planner can look for different solutions based on whatever I decide I'm trying to maximize or minimize. So in PDDL 2.1, I can call metrics in my it's in my problem file. Sorry, in my let me check that. Actually, I don't want to say something stupid. I'll check it later. I can declare something called metrics. I'll check in a second which file actually contains those metrics. But I can ask it to minimize or maximize some numeric fluents that I've been updating or defining throughout my problems. For example, here I can maximize something like maximize the distance traveled, or I can minimize, for example, fuel I've used, and that's a bit more of a realistic goal for our AI planner if we want to apply it to real-world problems. These don't replace the goals, so I still need to specify a goal state. I can't replace it with metric. The metric just tells the solver what plans are the best for us to look at. And support for metrics is wishy-washy. It's not the best, so we'll not be relying on them too much, at least in this current moment in time. And they're always fixing things and updating things. I mean that in the frame of reference of the UPF. So PDDL 2.1 in general has support for metrics, but the UPF that we're about to discuss doesn't have the best support for it. And if you want to know more about PDDL 2.1, you can go to the following page, which has a bit more information about all the different specificities of Yotam 2.1. So for those who have been to the lecture this week, I'm sure you've already seen the match seller problem. This is just like the most basic example when it comes to temporal planning. It's like the hello world, I guess, of temporal planning. So here's how we'll state our problem here. So let's say we have a cellar in our house where we have our fuse box. So whoever is older than me, if you know what a fuse box is, if you're younger than me, maybe you don't know what a fuse box is. But essentially, instead of breakers, we used to have something called fuses that would regulate or provide some safety measure to cut power if there's an overload in our house, in our home's electrical system. So a fuse, if it would have a current passing through it over a certain limit, it would burn out, and power would be cut, and you would have to go down and take a new fuse and replace that fuse. You couldn't just turn on a new breaker. So now I have this problem where I have a fuse box in my cellar, in my basement, and for some reason I live in the 1800s and I don't have natural or electric lighting in my cellar. So I'll need to use matches to light the cellar when I'm down there if I need to fix some fuses. So let's say my fuse box, I have 3 fuses that are burned out. I need to go down there, I need to fix those fuses. Let's assume now that I have a matchbox with exactly 3 matches somehow. And I'm going to take that matchbox down to my cellar, and I'm going to light those matches in order to be able to fix my fuse. Let's assume that I'm really scared of the dark, so if I lose any light, I will cry and run out of my cellar. We can only fix 1 fuse at a time because at the end of the day, if we hold 1 match in one hand, we can only fix 1 fuse with the other hand. So we need to figure out a way to sort of plan that will allow us to decide in what order do we light matches and in what order do we fix our fuses. So we see that we have matches that last for 15 seconds and give us light throughout. And it takes us 10 seconds to change the fuse. And we can't change the fuse if the light isn't interrupted during the time when we need to change the fuse. We'll get too scared and we'll run away. Let's see how we can write this using the unified planning framework that we've already seen in the last class. So first we just import the basic libraries. Once it runs, amazing. Now we'll define 2 user types. So we'll have a match and a fuse, as we could expect. And let's look at some fluents, some predicates here we want to define. Right now we're dealing with just the temporal planning problem. We're not going to do numerical planning until the next problem. So these are all just predicates, they're all Boolean predicates. So I have hand free and light. Hand free tells me that I have a hand free to fix a fuse. Light tells me that I have a match that's on, it's giving me light. And I have match used and fuse mended, which are correlated to a specific match or fuse. So if I turned on a match, it's been used. If I fixed a fuse, it's been fixed. It's been mended. I don't have to pass the bool type parameter to these fluents because the default will be bool type. So the UPF knows that these fluents are just Booleans if I don't pass any types to them. So I can check that here and see that as expected, light.type is bool. So now I want to define my action. So before the UPF, we had to use the instantaneous action class to define actions. Here we're going to use the durative action class to define new actions that have duration. So I call the durative action class to instantiate a new durative action object, which I'll call light match. And of course, I only need to pass the match to this action because I want to light that match. So once I light that match, we know that this action should last 15 units of time, 15 seconds. And the conditions and the effects of this action will be that at the beginning of the action, I should not have used the match that I want to light. And the effects will be that once I've used this match, once I've started the action, the match has already been used. So here you can see how I can declare the start, how we had the PDL 2.1 at start. Here we use just start timing in parentheses to declare that this should be true at the start. So again, after my first effect, which is the match we use immediately after the action begins, I also have that the light will become true. I'll have light immediately after I light my match, so immediately after the durative action begins. And the last effect is that once this durative action completes, once it ends, at the end timing, so at end, the light will be false, the light will turn off. I have a second durative action, fix fuse. So I pass the fuse that I want to fix to this action. This lasts for 10 seconds, 10 units of time. the condition that must be true for this action is that my hand should be free at the start of the action, and that for the whole time, for the entire duration of the action, I should have light. So in PDL 2.1, I just write overall to specify that. Here I have to write a little more, I write closed time interval, start timing, end timing. So it tells it that between start timing and end timing, light has to be true. Then my effects for this action are that my hand will not be free immediately after I begin fixing the fuse. So I'll start fixing the fuse, my hand's no longer free. At the end of the action, my hand is free again, and the fuse has been fixed. So that's the two last effects of this action. I can also use the UPF to specify durations, as mentioned before, that aren't fixed. So I can have intervals of time for my derivative actions, but for now, we'll just look at the fixed durations. So the actions take exactly 10 seconds or 15 seconds or so on. So we're done with our domain file. Now we can start declaring our problem file. So I'll just give it that name match seller. And I'll start adding my object. So here I add 3 fuses, I add 3 matches. I have to attach them again to the problem. So I've created a problem object, I've instantiated a problem object, and I have to associate everything in my domain along with the problem to that problem object. So this isn't like regular PDDL where I have 2 files. I have 1 file, and I have to specify everything into the problem objects. I add all my objects, my fluents, and my actions. Here, hand-free, I won't specify default value. Same for light. I'll just specify initial values for match use and fuse method. I'll just give them false. And to add my initial state, I just want to make it clear that in the beginning I don't have any light, so I have to at some point turn on the match in order to have light. So I've set the initial value of light to false. And my hand is free at the beginning, so I set the hand free to true, because I haven't touched anything yet. And I can see my full initial state, so I'm going to print the initial values for all of the predicates in my problem. I can see that light is false, hand free is true, and so on and so forth. Now my goal for this problem is to fix all the fuses. So I want to have fuse mended for all 3 fuses to be true at the end. So I add that goal, add those 3 goals to fuses. So again, we're working with Python, so we can just use lists and list comprehensions to make our definitions a bit faster. So we fully defined our problem now. We don't need to add anything else. We're done. Then we can check what kind of problem do we have. So we can run this problem.kind, can check that attribute, and it tells me that I have an action-based problem. So this just means it's a strips problem. I have continuous time. This is a new feature that tells us that we're dealing with a temporal planning problem. And I have 2 features we've already seen, negative conditions and flat typing. So negative conditions just says that I have some negative preconditions or some negative conditions in my actions. And flat typing just means that I'm using typing to get assigned new custom types for my objects in my problem. So again, this feature corresponds to the strips requirement. This feature corresponds to the derivative actions requirement, which is one we haven't seen yet. Those are the requirements you declare in the domain file. And negative conditions corresponds to negative preconditions, and flat typing corresponds to the typing requirements. And of course, if I wanted to, I can look at my whole problem and see what types I have, what fluents I have, and so on and so forth. Again, we can write our problem to PDDL files. So PDDL 2.1 also uses .pddl files, and it also works with the UPF. So we can write this problem to these files. And if I go into match seller, I can see exactly the domain. So the domain looks like this. As I said, the UPF automatically populates my requirements group with strips, typing, negative preconditions, and this new one, derivative actions. And this is how it looks when I'm looking at PDL 2.1. And similarly, I have my problem file, which is a bit shorter. Nice and sweet, we have that. So now, whoever hasn't done so, you can install the planner we'll be using in this tutorial, which is called Tamer. Tamer has pretty decent support for numeric and for temporal planning problems. So pretty much every part of this tutorial will rely on this Tamer planner. So if you take a few seconds, just install it before you run anything else. Otherwise, it won't really give you errors. If you're having trouble installing the UP Tamer, first of all, make sure you're inside the environment. If you're using the CogRub environment, ensure that you're actually in there when you're installing it. And if that doesn't work and you're using the environment and it doesn't update correctly, just add this line, add the UP tamer to the YAML file of the environment and just update the environment and it should work fine. There's some weird errors always with VS Code and Conda. I'm not really sure why, but it is what it is. Once we've done that, as usual, we can declare our planner. So in this case, we'll let UPF choose the best planner for this job based on the problem kind. And of course, it chooses tamer. And we can see what the tamer solver will return. So it'll tell us in the beginning, light the first match, or like whichever match. The order here was arbitrary in terms of the numbering. So like the first match, it'll take 15 seconds. Immediately after the start of the first action, we can start fixing the fuse because we'll have light. So notice here that we can have two actions running concurrently, which we couldn't have done using classical planning. Now with temporal planning, we can have actions running at the same time. But notice that the fixed fuse only occurs at time 0.01. So the reason for this is that the fixed fuse action can only be done once the light is on. And the light is only on immediately after the start of the light match action. So not immediately during the start, but immediately after. So it'll take it some discrete amount of time. So in this case, it's 0.01 units of time in order for the light to become true. Once that is the case, you can fix the fuse, it'll take 10 seconds. And then we'll notice that our planner told us to wait until the first match burns out before beginning to fix the second fuse, sorry. And this is because, as we've said, we get really scared if the light turns out while fixing a fuse. So we cannot start fixing the fuse with only 5 seconds left on our match. We have to wait until the match burns out and light a new one. So that's exactly what we see here. We'll finish fixing our fuse by 10.01 time. And at 15.01, I will start lighting my match because at 15.00, the first light match will cease. I will stop having light. I have to wait until 15.01 to do the next light match. Then that again, I fix my fuse, gives me 10 seconds. I have to wait 5 more seconds for the match to burn out. And then I can light a new match and then fix that final fuse. And that's it for this plan. Is there any questions so far about anything we've done?
Only the idea when you solve it, like if you're done with the fixing of doing 10 seconds, why don't you start immediately with the other one and like the other?
So we've declared that again, if my light turns off while I'm trying to fix the fuse, I'll get really scared and I'll run away. So I cannot just start fixing another fuse because it takes me 10 seconds to fix the fuse. Now, after I fix the first fuse, that's 10 seconds of light that have passed, and the match only lasts 15 seconds. So it gives me 5 more seconds, and that's not enough time to start fixing another fuse because it'll cut out the light in the middle, and then I will be able to complete my task. I've defined it here on purpose because if I go back to my action, wherever I defined it, I said that over the course of the entire fixed fuse action, the light has to be on for the whole time. So if it turns off for even 0.01 seconds, it won't take that as a valid condition for this action to occur. Okay, and again, I've created a Python file that runs this problem. So it just shows you how to easily call a Python file, which we will be working with in the homeworks to run this problem and solve it. Okay, so now we're going to be looking at a numeric planning problem. So we've shown an example of temporal. We're going to look at a bit more of a complex problem. And I'm sure a problem that the aerospace engineers and mechanical engineers or just general space lovers will enjoy a bit more. So now let's say that the Israeli Space Agency has launched a new satellite program. So here's the graphic I've made for this problem. So the Israeli Space Agency wants to launch a new fleet of satellites into space in order to observe a set of stars and of celestial phenomena. These satellites have instruments on them, and those instruments can take data, record data in 3 different modes. So in the mode of imaging, taking pictures, in a mode of a thermograph, which means they're just taking the heat signatures, and in a mode of spectrograph, which is taking in the light spectrum from the object. So these satellites, when they want to record data, the first thing they have to do is they have to turn on their instruments. So they begin by turning on the instruments on the satellite. Then they have to calibrate those instruments. So they have to point towards a calibration target. In this case, we'll have the ground station be that target. So they have to calibrate according to the ground station. And once the instruments are calibrated, they can start recording data. So they can turn back to whichever entities they want in the night sky and start recording data. The thing is that the satellite has a limited amount of fuel. So it starts with a certain amount of fuel. In this case, it was, let's say it's 240 grams of fuel. And every time I have to turn my satellite in order to point it either at the ground station or at the phenomenon or at the star, I use up a certain amount of fuel. Similarly, well, these numbers represent the amount of fuel that it takes me to move between two different pointing directions. And another constraint I have is that I only have a certain amount of data storage on my satellite. So let's say that my satellite has, it goes 500 gigabytes of data storage. Every time I record data, I take up some of that storage. So I'll need 150 gigabytes in order to take a picture of the phenomenon, and I'll need 250 gigabytes to record images of the star. So my goal here is that with this first satellite, we'll have one satellite in space. It'll have an imager, an instrument with the imager mode on it. And as like one ground station, there's one star and there's one phenomenon. And we want this satellite to calibrate its instrument and record data from all of the necessary objects. So we begin by, So we'll begin by defining some types. So here I have 4 types that I want to define. So I have a satellite, I have a direction. So which direction is my satellite pointing? We'll treat these objects, the phenomenon and the star, as directions, just for the sake of simplification. We don't have to call them anything else. So we'll just say the directions in which our satellite is pointing with an instrument. And we have modes. So our instrument can have multiple modes. It can have imaging, it can have thermograph, and so on. And usually each satellite will have one instrument that can have multiple if we really want to. So now we'll start defining some predicates. So we'll have both numeric and Boolean fluence in this problem. We'll begin with the predicates. So I have a bunch of predicates here. We have onboard, so checking that the instrument that I've declared is on the satellite. We have supports, so checking that my instrument can conduct that certain type of data measurements, whether it's imaging or spectrograph and so on. Pointing, which tells me which direction is my satellite pointing at. Is it at the star, the phenomenon, the ground station? Power avail. So in order to turn on my instrument, I need to have power available from the satellite. So that is a Boolean that tells me that. And as soon as I turn on my instrument, of course, my satellite will have power going point to that. So when I have more power available, I have power on. So this tells me whether my instrument has received power or not. Calibrated, which tells me have I calibrated this instrument according to the calibration target. Have image, which tells me that I've recorded data of this mode from this direction, from this object. So have I recorded images from the sun, from the star, for example? And I have my calibration target. In this case, it's going to be the ground station. But this allows me to say which direction is the direction in which I have to point my satellite in order to calibrate the instrument. That's all these. And then we have some numeric fluence. So these are the numeric variables that will change over time. We can use to kind of set constraints on a problem. So I have data capacity. So this tells me how much total data storage does my satellite have. So it begins with 500 gigabytes, but I can store it here. I have my data fluent. This tells me how much it costs me to record data in a certain mode, pointing at a certain object. I have slew time. This tells me how much fuel do I need in order to turn my satellite between two pointing directions. I have fuel, which tells me how much fuel does my satellite have left, and fuel used, which records in total how much fuel have I used, how much fuel. If I have multiple satellites, for example, this will tell me how much fuel is used across all satellites. And I'm setting these all to just be integers, just for the sake of simplification, but I could change this int type to a real type, and it would allow me to use real numbers. So those are my numeric fluence. I just forgot to mention that this problem is based on a real problem that was used in an international planning competition. So at IPS 2002, the artificial planning and scheduling conference that occurred in 2002, they used this exact domain, the satellite domain, as one of the competition domains for the international planning competition in that year. So I didn't just pull this all out of my butt. This is a real benchmark domain used to test various planners. Now we'll look at our actions to that digression. Here again, we're only using instantaneous actions. We're not doing temporal planning here. We'll just do some numeric planning. And if I want to turn my satellite between 2 points, I need to have some preconditions, not conditions. These are just preconditions because it's instantaneous. But those preconditions are that my satellite should be pointing at the original direction. The two directions shouldn't be the same direction. So that's what this equals tells me, not equals. And the precondition here, that we see the first numeric precondition, is that my fuel should be greater, the fuel cost, or the slew time, the cost of fuel for moving between these two directions should be less than the total fuel that I have in my satellite. So I use this GE, it's greater than or equal to say that the fuel of the satellite should be greater than or equal to this slew time between those two directions. So that just limits me to only turning between two directions when I have enough fuel to do so. Then I have the effects. So again, the satellite will not be pointing in the original direction anymore. It'll be pointing in the new direction. And I have some numeric effects. So the fuel in my satellite will decrease by the slew time. So I can add it like that. And the fuel used parameter, which I'm using to sort the total fuel used across all my satellites in my fleet, I increase it by the slew time to say I've now used this much fuel. Then I have two similar actions for switch on and switch off. This allows me to turn on and turn off my instruments. So if I want to turn on my instrument, the conditions I need are that that instrument should be on board that satellite. There should be power available from that satellite for the instrument. And for the conditions, once the instrument is turned on, the power on becomes true, it has power. Power available from the satellite is no longer true because I've directed all my power to that instrument. And the instrument begins as uncalibrated if I turn on the instrument. And switch off does just the opposite. It just turns off the instrument, brings power back to the satellite. I have calibrate. So if I'm pointing my satellite towards a calibration target, in this case, the ground station, I can calibrate my instrument so that I can start recording data. So that's just represented here. Pretty straightforward. And finally, I have my take image action. This allows me to record data. So it has all of the predicates that you'd imagine it would have. So instrument has to be on and calibrated and on board the satellite and so on. And the numeric condition that I add here is that the data cost of recording data in the direction of the SAR, the phenomenon, using whatever mode, so imaging and thermograph, it has to be less than the total data available on my satellite. So my satellite's data capacity is stored in this data capacity parameter, and I have to make sure that it is greater than or equal to, it's GE, greater than or equal to the data cost of recording data in that direction. Once I conduct this action, the effects are that I'll have the image in that direction, in that mode, and my data capacity will decrease by whatever data I've recorded, and the total data stored across all satellites will increase by that amount of data. So that's it for the actions. Any questions so far? Great. So I'm done defining my problem file, my domain file, sorry, for this problem. Now I can start building the problem. So again, I call the problem class to instantiate a problem object. I call a satellite, I instantiate a satellite, an instrument, the mode for the instrument, which is imaging, and 3 locations. So the ground station, the star, and the phenomenon. I just put them all on a list called objects, and I add those objects to my problem. Next, I just add all my fluents. So I'll initialize them, most of them to be false, except this one fluent, this one predicate, sorry, it's called power avail. In the beginning, for all satellites, power should be available. The instruments shouldn't be on. So that one is the only one that will start at true automatically for all satellites. And to add the numeric fluents, I can pass the initial values as numbers. So I can either not pass any value, for example, data capacity, I didn't pass any value for the initial value as default, but I can, for example, add the data parameter as initialized to 0, slew time initialized to 0, data stored, and so on, if I want to, 0, whatever other parameter, whatever other number. And I just add those actions. And now I want to add the initial values for predicates. So instrument 0, instrument that I added supports imaging, that's true. The ground station is the calibration target for the instrument is true. Instrument onboard satellite, power is available. We didn't need to call this one because we've already declared that power available is true automatically for all satellites, but I've added it here just for redundancy and clarity. And the satellite begins pointing at the phenomenon. So if we go up to the image, we see that our satellite begins pointing this way. Then I can initialize the values of my numeric fluence. So my data capacity of my satellite, as we said, was, I guess it was 550 gigabytes. The fuel in my satellite begins at 240 grams. The data cost of recording images from the phenomenon is 150 gigabytes. And similarly for the star is 250 gigabytes. And the last thing to do is add those slew time values using a dictionary, which I call fludict. Usually, if we have to add geometric properties, for example, if we're adding the slew times, or if we're solving a graph that has distances, we'll use just the dictionary to record those values and then add them in a loop. So I can add the slew time between the 2 points by defining what those values are in the dictionary and just iterating using a double for loop. I think it's much easier just to do for loops than to write out every single one by hand, but feel free to do whichever you prefer. Finally, at the end, we just have 2 goals. So we just want to record data, have data be recorded from the star, and have data be recorded from the phenomenon. So I mentioned before metrics. So ideally, would have liked to use the metric of minimize the amount of time that it takes to do everything. Or minimize the amount of time, or minimize the amount of fuel I have to use. For example, that's a very common metric that we might want to use. Unfortunately, at this very moment, the UPF doesn't have great support for these metrics. They're not so integrated very well. Every planner that we'll use will just do something called satisficing. So it'll just find a satisfactory solution to the problem rather than the optimal solution. There are certain planners that have some sort of optimality variation. We saw the best downward has an optimality guaranteed version, but that's just optimality in terms of number of actions. It's not in terms of any parameters. But hopefully in the future, and I've seen right now that the UPF is getting updated all the time. It's because it's so new and it was only initialized in 2020. We can see that I've seen that they're starting to add a bit more support for metrics. Hopefully in the course of the semester, there'll be support available so we can look at more interesting problems. But I digress. You can write these problems again to PDL files. If I go to satellite num, I can see exactly those files. They look here. Now we have a new, 2 new requirements here of numeric fluence and quality. Quality just allows me to equate between 2 different parameters. So, for example, the action of slew time, of turn 2. If I want to turn between the directions, I have to make sure that those directions aren't the same direction. So I use not equals. So that just adds an equality requirement. And using any numeric variables, I have to add a numeric fluence requirement. So here I've just defined a helper function just to show you guys the result of the problem of the plan. So once I call Tamer to solve this problem, it'll give me this list of actions to do. And I can see that my initial fuel level began at 240 and my initial data capacity began at 550. And this is how much they decreased to. So I wanted to make sure that my fuel didn't decrease below 0. Luckily, I have 48 grams of fuel at the end, and my data capacity finishes at 150 gigabytes. Luckily, it didn't go below 0. So that was just a sanity check to make sure that our plan is valid. And again, I create a Python file to run from. And nicely for these certain types of numeric planning problems, the VS Code extension for PDL can solve them and can show you again the list of actions to take. But even nicer, it actually provides graphs that show you over the course of the plan. So here's the point of time, it's not really time. Over the course of the action of the plan, it shows you how your different numeric variables will change. So if you want to see how your fuel capacity changes over time or how your data capacity changes over time, you can see it here. In this case, you can see that our fuel used ends up being 121 grams. So actually here, it was able to find an optimal solution. So using only 121 grams of fuel is the optimal answer. Whereas using UPF, we weren't able to obtain an optimal answer. We actually used up 192 grams. So here, this number is 48, where it should be a bit higher if we use the PDL extension solution. But that's just because they have support in the PDL extension. for optimal solving, and unfortunately, I don't have it for the UPF at this moment. Just one last thing, the metric. So, okay, the metric is declared in the problem file. Here we go. And here, I was able to declare it for this problem, metric minimize fuel use. So the PDL extension looked at this file with this metric and said, okay, let's find the plan with the lowest amount of fuel used. And that's exactly what it did. We've run out of time. There is one more example here that I encourage you to look at in your free time. It involves temporal planning. So now we take our satellite problem and we ignore the numeric variables, ignore fuel, ignore data, and just say that there are certain actions that take up a certain amount of time. Now we want to figure out how long we'll need in order to conduct data recording over all these objects. So that's what this problem covers. I encourage you to look over the file in your own time. I don't want to take up more time. But essentially, if I run it, I will see that I have a solution with a list of actions. They all occur one after the other. In this case, they all take a certain amount of time, and you can see for yourself what it does. Here, I could have actually just declared this problem because all these actions happen to be sequential here. I could have just used the classical planning representation for this problem and simplified it. But if I wanted to add, for example, a second satellite, and I wanted to minimize my total time to record data from everything, then the solution that wouldn't have been classical anymore. It would have been some plan where the two satellites would have been working at the same time. So that's an example of why temporal planning is more useful for realistic problems, where we can optimize according to multiple different agents doing multiple different tasks. So feel free to look over that in your free time. We're done for today. The homework will include some temporal planning problems. So you'll probably have to reference files here to just understand how to go about encoding them. And again, it'll be released tomorrow and due in 2 weeks. So hopefully it gives you enough time. If you need an extension, just reach out to me and we'll work it out. All right, thank you guys.